Look around you, what do you see? You might spot a window, a drinking glass, or even the screen you're reading this on. What do these objects have in common? They're all made of glass, a material so commonplace that we rarely stop to ponder its remarkable properties. The most obvious, of course, is its transparency. But have you ever wondered why glass lets light pass through while other materials like a wooden table or a brick wall remain stubbornly opaque? The answer lies in the fascinating world of atoms and photons, the tiny particles that make up everything around us, including light. Let's embark on a journey to unravel the science behind glass's transparency, exploring the fundamental laws of physics that govern this everyday phenomenon. To understand why glass is transparent, we must first understand the nature of light itself. Light is not just a simple beam, it is a complex phenomenon that has intrigued scientists for centuries. Light, that ethereal phenomenon that bathes our world in warmth and color, is a form of electromagnetic radiation. It encompasses a wide range of wavelengths, from the visible spectrum that we can see, to the invisible realms of ultraviolet and infrared. Imagine light as a wave, similar to the ripples on a pond, but instead of water, it's made up of oscillating electric and magnetic fields. These fields interact with the materials they encounter, influencing how light behaves. These waves of light travel at an astonishing speed, the fastest in the universe, covering approximately 300,000 kilometers in just 1 second. This incredible speed allows light to traverse vast distances in the cosmos. When these waves encounter matter, they can be reflected, absorbed, or transmitted, depending on the properties of the material. The interaction between light and matter is a fundamental aspect of our understanding of the physical world. Transparent materials like glass allow light to pass through them with minimal absorption or scattering. This unique property makes glass an essential material in various applications, from windows to lenses. But how does this happen at the atomic level? The answer lies in the unique structure of glass. The arrangement of atoms in glass allows light to pass through without significant hindrance, making it an invaluable material in both everyday life and advanced technology. Imagine a bustling city with skyscrapers representing atoms. In most solid materials like the aforementioned brick wall, these atoms are arranged in a highly ordered repeating pattern, like a well-planned city grid. This rigid structure is what makes these materials opaque. When light waves encounter this organized lattice, they get absorbed by the atoms or bounce off in different directions, preventing them from passing through. Glass, on the other hand, is different. Its atomic structure is more akin to a frozen liquid, a state known as an amorphous solid. It's like the city suddenly froze mid-activity, with buildings haphazardly placed, lacking any long-range order. This seemingly chaotic arrangement is the key to glass's transparency. Section 4. Light's journey through glass. A game of billiards? Not quite. While billiards is a game of precision and angles, the journey of light through glass is a dance of physics and nature. Now let's picture a beam of light approaching a sheet of glass. This isn't just a simple interaction, it's a fascinating process that reveals much about the nature of light and materials. Unlike a solid wall, where light waves get blocked by the organized atoms, glass presents a different scenario. The loosely packed, disordered structure of glass allows light to interact differently. This disordered arrangement is key to understanding how light can pass through. Instead of being absorbed or reflected, the light photons essentially squeeze through the gaps between the atoms. It's almost like the light is threading a needle through the fabric of the glass. Think of it like this. Imagine trying to navigate a crowded room. The way you move through the crowd can be compared to how light moves through glass. If everyone is standing in neat rows, it's difficult to make your way through. The organized structure acts as a barrier, but if the crowd is more haphazardly arranged, you can weave your way through the gaps. This is similar to how light navigates through the disordered structure of glass. This is a simplified explanation, of course. The actual process is more complex and involves intricate interactions at the atomic level. The actual interaction involves the light's energy being absorbed and re-emitted by the electrons in the glass atoms. This absorption and re-emission process is what allows light to pass through. However, the net effect is that the light continues its journey through the material, maintaining its path but with some changes, albeit with a slight delay due to the time taken for these interactions to occur. Which is why we see objects on the other side of the glass. This delay is imperceptible to us, but it's a crucial part of the light's journey. Section 5. The limits of transparency, when glass turns opaque. While we perceive glass as transparent, it's important to note that it's not transparent to all types of light. Different wavelengths of light interact with glass in various ways, leading to some fascinating effects. Ultraviolet radiation, for instance, which is responsible for sunburns, is largely blocked by glass. This is why you don't get sunburned when sitting behind a window, even on a sunny day. This is because UV light has a higher energy level than visible light. The higher energy photons are absorbed by the glass, preventing them from passing through. The electrons in the glass molecules absorb this higher energy, preventing the UV radiation from passing through. This absorption process is crucial in protecting us from harmful UV rays. Similarly, infrared radiation, which we perceive as heat, is also partially blocked by glass. This is why you can feel the warmth of the sun through a window, but not as intensely as if you were outside. This is why greenhouses work. They trap the sun's heat inside. The glass allows visible light to enter, which warms the interior surfaces. The glass allows visible light to enter and warm the interior, but the infrared radiation emitted by the heated objects inside is partially blocked, keeping the greenhouse warmer than the outside environment. This selective transparency of glass is what makes it such a unique and useful material in various applications. Section 6. Glass, a versatile material with surprising applications. From windows and bottles to fiber optic cables that carry vast amounts of information across continents, glass plays a vital role in our modern world. Its transparency, combined with its strength, durability, and ability to be molded into various shapes, makes it an incredibly versatile material. Fun fact: did you know that glass is actually 100% recyclable? It can be melted down and reformed countless times without losing its quality. This makes it an environmentally friendly material, especially compared to plastics, which often end up polluting our oceans and landfills. Section 7. A glassy conclusion. More to discover. The next time you gaze through a window or sip from a glass, take a moment to appreciate the wonders of this seemingly simple material. Glass's transparency, a consequence of its unique atomic structure and its interaction with light, is a testament to the elegance and complexity of the natural world. And while we've uncovered some of the secrets behind glass's transparency, there's still much more to discover. Scientists are constantly developing new types of glass with enhanced properties, from self-cleaning windows to super strong glass that's thinner than a human hair. The future of glass, it seems, is as clear as ever,